Right, so first I would like to thank the organizers for the chance to talk here today. What I'm going to talk about is joint work with Adrian Constantin. And so basically we're looking at traveling wave solutions for 2D Euler on the sphere and trying to understand their properties, in particular stability properties. And an important class of solutions is given by the Rosby-Horowitz. So I'm going to start by just setting up the equation. So we are on the sphere. The coordinates are, this coordinate is P, and this coordinate is theta. So on the sphere we have the Laplace-Beltrami operator, and the spectral resolution of this operator on the sphere will be important. So let me recall it. The eigenspaces of this operator will be denoted Ej, and they have a dimension k plus 1. So obviously E naught is just the constant, so it's not very interesting. E1 is made up of 3 solutions. It's generated by, let me get it right, cosine theta P, sine theta, and cosine theta minus I phi. And so since the Laplacian commutes with rotation in the zonal direction, you can always expand in Fourier mode in the phi variable, which is what we did here. And so it's true for the jth eigenspace as well. So a basis is provided by functions that are denoted y, m, j, where this is the eigenspace number, and this is the Fourier mode in phi. So this is classical, but it will play an important role, so I wanted to recall it. Okay, so next we are considering the we are considering the 2D Euler equations on the sphere. So for the stream function psi, it can be written as follows: psi and here omega is the rotation speed of the frame of reference we are considering. Omega equals 0, corresponding to the Galilean frame. So we are particularly interested in stationary solutions. And they solve the following equation: Laplacian psi equals f of psi minus 2 omega sine theta. And here the function f can be any function. So if you solve this elliptic problem, then you are a stationary solution for this Euler equation. So in the Galilean frame, this corresponds to a solution that rotates at constant speed omega. Okay, so we are interested in such objects. We want to know more about them. And of course, which ones are stable is the big question. Okay, so maybe I can do that here. So what are solutions of star? Let's call star this equation. What are solutions of star? So you have the obvious answers, which are first zonal flows. Which corresponds to choosing psi as a function of theta only. Okay? And the other obvious answer is eigenfunctions of the Laplacian. So if psi is in EJ, what you can choose here is for f simply the function yes, exactly. Yeah. J times J plus 1. And then you have the Rossby-Harvitz solutions. Which are of the following form. E equals alpha theta. So this corresponds to omega equals 0. And if you want omega non-zero, you should take psi to be alpha sine theta plus y theta, where alpha is omega over 1 minus k plus 1. Okay, and as far as I know, these are the only explicit solutions that are known as solutions to this problem. And both classes of solutions are physically relevant. Well, zonal flows are, of course, observed, but Rossby-Harvitz solutions are also observed in the atmospheres of the planets of the solar systems that do have an atmosphere. So let me give some references. And let me start with some works in the physical literature. So of course, Rossby and Harvitz, who found the equivalent of these waves in the beta plane model, which was then fully understood by Craig for the 2D Euler on the sphere. Then there are some observations of Rossby-Harvitz waves. So there is toweling on Earth, and there is Yamakazi, Mazaki, Hoffman. So this is for Earth, this is for the solar system. And then there is a work by, so on the stability of Rossby-Harvitz. There is work by Bénard, but which is rather inconclusive. So this is for physics. As far as math, there is a very nice work by Michael Taylor, who develops the theory of the 2D Euler equation on the sphere, basic things, local well-posedness, and also has interesting results on the stability of traveling waves. And then there is Cheng Mahaloff. who considered the behavior of the 2D Euler equation on the sphere in the limit of a large rotation parameter, and he observed convergence to zonal flows after some averaging. And then there is a book by Skiba, which is a classical reference for 2D Euler on the sphere. Of course. That's true. Yes, that's true. That's true. Yeah, that's true. That's also an interesting class of solutions. But indeed, psi is smooth here. But of course, point vortices are important. And then they solve an integrable equation for which you also have many explicit solutions. Thank you. All right. First result is on the symmetry of solutions of theorem. So once again, this is joined with Adrian Constantin, as are all the results that I will present today. And so what this is saying is that if the function capital F that you have here is such that capital F prime is bigger than -6, then C is zonal up to a rotation. So this is remarkable, right? If the function f here is not allowed to have a derivative that is too small, then the solution has to be zonal. But of course, everything is invariant by rotation. So this can only be true up to a rotation on of the 2D sphere. Okay. And then another interesting observation about stability. First result. So also with Adrian, so if f prime is bigger than -6, then psi is stable. So if f prime is bigger than -6, well, first then this implies that the flow has to be zonal, and then it also has to be stable. Yes. It's just Euclidean isometries act on the sphere. So you just turn the sphere around, right? But yeah. I mean, what I'm just saying is, suppose you have a solution on the sphere, right? Then you can rotate the sphere, say in the direction of phi, for instance, and then it remains a solution, right? So yeah. Yeah. Yes. So maybe let me spell it out. What I mean is that psi. Yes, exactly. That's what I mean. So if you choose the polar axis correctly, then it's zonal. But that's the best you can hope for. You cannot hope for psi to be zonal with a distinguished polar axis, but it has to be free. So if you give me a solution with f prime bigger than -6, then I can find a polar axis around which this solution is zonal. That's what I mean to say. Right, yes. So that's just the invariance of the equation. Is this function here? Yes, yes. Yeah, yes. So that's everywhere. Point-wise, everywhere on the sphere. Yes. Same here. Yes. Yeah.
If psi has a derivative other than
It's f. F has a derivative which is bigger than -6. F is the function here. So it's a function. F is a function. So yeah. Yeah, so psi. Psi is the stream function of the traveling wave, right? It satisfies an elliptic equation on the sphere for a given function f. F might depend on psi, does depend on psi. Yeah.
this board,
Yeah.
there is no
Yeah, so sorry. We're looking at solutions of star. We're looking at solutions of this elliptic problem. So that's not what I'm saying. I'm saying if there is a solution with f prime bigger than -6, then it is zonal up to choosing the correct polar axis, and it is stable.
Do you suppose that f is a linear?
No.
So it may have derivatives which vary for
So if you want, I can replace. So what I mean, f prime bigger than -6 means f prime of x bigger than -6 for any x. Sorry, f prime of psi for f prime of psi of x. Yes. All right. So this. So I'm coming to that. That's. Oh yeah. So maybe that will help. So these are actually classical results for general manifolds. So if you take a Riemannian manifolds, the same results hold with a -6 replaced by lambda, which is the first eigenvalue of the Laplacian. First non-zero eigenvalue of the Laplacian. So for the sphere, -6 is the second eigenvalue. I recall the right? the second eigenvalue. Oh yeah, I should say Laplacian on EJ is J. That's the eigenvalue associated to the eigenspace EJ. So for the sphere, -6 is the second eigenvalue. So there is an improvement which is related to just the very symmetric nature of the sphere, which is locally symmetric space. Yeah. So J equals 1. So the general theory, so the general theory or general manifolds is due to Arnold as far as stability goes, and as far as symmetry, it's Konstantin Drivas Ginsburg. So this is classical Arnold stuff, and this is a more recent paper. And of course, for something like zonal to make sense, you need to make some assumptions on the manifold. It has to have some symmetry, but I don't want to go into that. But the remarkable thing is that for the sphere, you go from the first eigenvalue to the second eigenvalue, which is a smaller number. So it's a sharpening of the result. Well, the torus is as well. It's so the torus is, yes. Actually, that's a good question. So all the points in the torus are equivalent, but not all directions on the torus are equivalent. While on the sphere, not only all points are equivalent, but also all directions are equivalent. So it's more symmetric. Okay, so that's an interesting improvement, and it's also pointing towards the importance of the Rossby-Hurwitz solutions of degree 2, because then f prime equals -6. So the Rossby-Hurwitz solutions of degree 2 are minimal if you measure the complexity in terms of f. These are the the simplest. These are the simplest traveling waves that are not zonal, because if you take f prime a tiny bit smaller, then they have to be zonal. So these are the simplest non-zonal objects. And they are also on the threshold to instability, because once again, if f prime is bigger than -6, then the flow is stable. So they appear as very important objects for the dynamics. And to these we will now turn. Maybe I have to use that. Do you guys know if I'm supposed to use that to J? Let's try. I'm not. It's this one. Of course, thank you. All right, so I hope this convinced you that the Rossby-Horowitz waves of degree 2 are important objects, and now I'm going to discuss their stability. Yeah. Oh, it's the other way around. It's the ones that have index 1 are stable, but this is trivial. This is conservation of angular momentum. The ones of degree 2 are on the threshold, and I'm going to tell you something about them. And of course, the higher the index, the more complex the waves. So, you know, the more unstable they become, though rotation can help. But this is a difficult question. And what I'm going to tell you about is the degree 2 waves, which are, once again, on the threshold, and for which we can give a part of an answer. And I mean, I'm going to tell you the story. Yeah. Nonlinear. But linear stability or instability is also an interesting and difficult question, right? But for these ones, we're going to talk about the nonlinear instability. Okay, so Rossby-Horowitz of degree 2, they look as follows. So they look like psi with E2, so meaning an element of the second eigenspace, minus 2 omega sine theta. Omega is the rotation speed. So theorem the set of Rossby-Horowitz waves of degree 2 is stable. Meaning the i.e. E2. If you start close to this set, you remain close to this set for any time. And so this is true in H2. The two derivatives in L2. So it's L2 for the vorticity. But we expect more to be true. And what we could also prove is that the solution y 0 2 omega theta is stable for the flow given by the 2D Euler equation. So if you start at time 0 close to this solution, then you remain close for any subsequent time. Okay? And what we conjectured is that this is true for any y in for any Rossby-Horowitz wave. But there is an obvious modification that you need, namely, or that say stability holds. So in other words, if at time 0 psi at t equals 0 equals some y minus 2 omega sine theta, then for any positive time, psi plus a perturbation of size epsilon, then for any later time, psi of t is y. But of course, what can happen is that y is rotating rotated in the zonal direction, so possibly rotated. Minus 2 omega sine theta plus O of epsilon. Okay, so this is a loose notation, but I hope you understand what I mean. You start with this Rossby-Horowitz wave of degree 2, which is just the general form. And at a later time, what can happen is that the wave has turned around the polar axis, it's this piece, and otherwise you're still within epsilon, which is the size of the initial perturbation. Sorry? What do you call the drift? Oh, how much you rotated? No, because you see what happens is that if you're perturbed by epsilon, you can actually affect the rotation speed, right? What can happen is you perturb by epsilon, but now the wave is very close, but it's rotating at a different speed. So after a long enough time, epsilon t, yes. Yeah. Okay, so there is like a heuristic argument towards this conjecture that can be found in a paper by Wuri-Soetisno and Shepard, an old paper in the 90s, I guess. Oh, there is an H? I'm not sure. Anyhow. Right, yes. Did I get the spelling right? Yes, okay, all right. So this conjecture was then partly proved by Cao, Wang, and Zhuo, but this was just a few months ago. So what they were able to do is to prove this result, allowing for any rotation, not only a rotation around the natural polar axis. Okay, so I can just tell you a few words about the proof. So the proof so of course the first thing you do is you use the conserved quantities. First, the conservation of angular momentum gives you that the projection on the first eigenspace of the Laplacian of psi is actually is it constant? It's not constant, but it's you can solve exactly. It's not constant because we are in a rotating frame, but in the Galilean frame, it's constant, so you can compute it. And then you have conservation of the kinetic energy, and you have conservation of the entropy. And if you put all of this together, it gives the first statement of the theorem. But to get to the second statement, you need to use, yeah, it's, so these are all L2 quantities, and you can write everything. The kinetic energy is, roughly speaking, grad psi squared. This is Laplacian psi squared, except that there should be some omega. And if you write this explicitly, and you work a little bit, you get the first statement of the theorem. As for the second statement, so this gives first statement. As for the second statement, what you need to do, you need to use more conserved quantities. So what's usually called Casimirs associated to the Euler equation, namely I of psi, which is the integral of psi, Laplacian psi plus 2 omega sine theta to the p sigma. This is conserved, so this is I sub p. This is conserved for any p. You can take any p. Sorry? Oh, what do you call absolute vorticity? Oh yeah, yes, exactly. It's the level set of the. Yes, you mean the level sets are conserved of the yeah. Yes, that's true. And so then what you can do is you can expand psi in spherical harmonics. Okay. Okay. And what you know is that sort of only j equals 2 matters for what we want to do, because we learned from the first point that this set is stable. And now what we want to prevent is energy to redistribute within the second eigenspace. So it suffices to focus on j equals 2 here. And then you can think of psi as a, or rather IP of psi, as a polynomial in the CMJ. And then you need to work out exactly what these polynomials look like for various values of p. And then you make sure that controlling these polynomials actually reduces to a control of the CMJ in the case of interest. So I won't give any further detail, but that's really the core idea. That's all I wanted to say, and I thank you for your attention. Thank you. And I should say, if since the many physicists or applied mathematicians are in the audience, if you have any suggestions of interesting related problems or interesting waves whose stability should be thought about, I would be very grateful.